we need to determine whether the series is convergent or divergent. We're looking at the series of n squared plus 6n, all divided by the square root of n to the 7th plus n squared. Now, when we look at this series, we realize that the expression for the term is rather complicated. That's a good clue that using a comparison test is going to be a good idea. I am going to let a sub n be the term in the series we are given. Then what I want to do is choose a new term, b sub n, to compare with this series. When I choose the new term, I focus on the dominant term in the top of this fraction and the dominant term in the bottom. So on the top, I notice that n squared has the largest exponent, and on the bottom, n to the 7th has the largest exponent. What this means is that when n gets very, very large, those two terms become the most important. So we're going to choose b sub n to be n squared divided by the square root of n to the 7th. Notice I can simplify this. This is n squared divided by n to the 7/2, or in other words, 1 divided by n to the 3/2. We know that the series of the terms b sub n is equal to the series of 1 divided by n to the 3/2 power is a p-series with p equal to 3/2, which is greater than 1. So the series b sub n converges. What we are hoping is that we can use a comparison test to show that the series a sub n also converges. Now we know that the direct comparison test, we would need to show that a sub n is less than or equal to b sub n. However, this is not at all clear. So instead, let's use the limit comparison test. For the limit comparison test, we need to look at the limit as n approaches infinity of the fraction a sub n divided by b sub n. In other words, the limit as n approaches infinity of n squared plus 6n divided by the square root of n to the 7th plus n squared divided by 1 divided by n to the 3/2. In other words, we have n squared plus 6n divided by the square root of n to the 7th plus n squared multiplied by n to the 3/2 divided by 1. I can distribute on the top of this fraction. We get n to the 7/2 plus 6n to the 5/2, all divided by the square root of n to the 7th plus n squared. Now, in order to take the limit as n approaches infinity, I am going to multiply the top of this fraction by 1 over n to the 7/2, and I'm going to multiply the bottom of this fraction by the same thing, but I'm going to write it as the 1 over the square root of n to the 7th. So we have the limit as n approaches infinity of 1 plus 6 divided by n over the square root, and inside this square root I'm dividing each term by n to the 7th. We have 1 plus 1 over n to the 5th. As n approaches infinity, we know that 6 over n approaches 0 and 1 over n to the 5th approaches 0. So our limit overall is 1 plus 0 divided by the square root of 1 plus 0, which of course is just 1. Now the important thing about our answer here is that our limit is not 0 and our limit is not infinity. We can conclude that by the limit comparison test, because our series b sub n converges, our series n squared plus 6n divided by the square root of n to the 7th plus n squared also converges.